Hello and welcome to Tonight at 8 from the RSGB. We've all seen how consumer electronics goods have been getting steadily more sophisticated and cheaper, and now that technology has started to make its way into more specialised equipment for radio amateurs. One such piece of equipment, which has only recently become very affordable, is the Vector Network Analyzer or VNA. But what is a VNA and what can it do for us? Alan Wolke, W2AEW, is not only a keen radio amateur, but is also a professional RF applications engineer. And so who better than to tell us what we can do with a VNA? Welcome to Tonight at 8, Alan.
Well, thank you very much, David. Happy to be here. Tonight we're just going to take a brief look first at what a vector network analyzer is. We'll kind of define that and what its applications are. And then we'll dig in a little bit deeper into the NanoVNA, which is so affordable and so useful for all of us hams.
Yeah, we're really looking forward to it as well. And before Alan's presentation, a reminder that if you're watching this on Monday the 12th of April, then this is live. And you can add comments and ask questions on either BATC or YouTube at any time during the presentation or straight afterwards. Please include your first name and your call sign, if you have one, within the message. Also, please note that you can make this video stream fill your screen on most devices, usually by double-clicking on the picture or pressing the full screen button. But now it's time to go back to Alan and learn all about the VNA.
All right, thank you very much. So again, we're going to cover just an intro to what vector network analyzers are and the NanoVNA. And I am Alan Wolke, W2AEW. I serve as the technical coordinator for my part of the world here for the ARRL in the US. And I've got a little bit of a YouTube channel here we could talk about a little bit later. But let's start chatting about VNAs. So here's our agenda tonight. Why do we want to talk about this? Well, the main reason is that these ridiculously inexpensive, meaning $50 or $60 US, the NanoVNAs, now make vector network analyzers accessible to the hobbyists like ourselves. So first, we'll talk about what a vector network analyzer is, what it's good for, what we can use it for, and then finally take a look at the NanoVNA itself. So first, what is a VNA? Well, if you look up online and you type into Google and ask what a vector network analyzer is, you may find something like an instrument that measures the magnitude and phase of the reflection and transmission properties of the ports of a device versus frequency. Well, that probably didn't help most of us. Okay, so let's break this down and try to make it a little bit clearer so you can all understand what a VNA is. So a VNA is typically an instrument that's used to characterize RF devices. Okay, that's simple enough. And it used to only be used by professional RF engineers in professional environments due to the cost. These two devices here in the upper left are $10,000 to $15,000 VNAs, and those are inexpensive professional VNAs. Professional units can cost many thousands of dollars, so these inexpensive ones, again, a few $1,000s US. This 4-port top-of-the-line unit here from Keysight, nearly $250,000 US. So they're pretty pricey devices and typically not something that most hams would have access to. Now, if you do any research online to figure out how to use a VNA or bring up application notes and things like that, you're going to find lots of acronyms and terminology. So we're going to define a couple of those things so that you can be familiar with that when you're doing your own research. The first is a DUT. What is a DUT? The DUT simply stands for device under test. In our case, it could be an antenna system, a filter, an amplifier, etc. Now, any DUT is going to affect the signal that goes through it if it's a 2-port device. It's going to have some effect on it. It's going to filter it. It's going to amplify it. It's going to distort it or something like that. But also the input impedance to a DUT is going to affect the signal that's applied to it. Like the DUT could be an antenna or an antenna system, so that may affect the signal that's applied to it. And that's due to impedance matching issues. And we're all taught that to get the maximum power transfer from any kind of a source into any kind of a load, we want the source and load resistances to match. Now, from an RF standpoint, it gets just a little more complicated. We want essentially to have a complex conjugate relationship between the source impedance and the load impedance in order to get maximum power transfer. We're not going to talk too much about the complex math and things like that here, but just suffice it to say that we typically need specialized instruments in order to measure these types of things, in order to be able to design things like matching networks and things like that. Of course, we can use the VNA to do things other than more complex jobs like designing a matching network, but I wanted to at least lay the concepts out here. So it helps when we start talking about RF to think of signals as waves. So if we think about a wave can have a magnitude and a phase. Phase can just be thought of as effectively a delay, right? We can see these two signals that are shown here have got different magnitudes and a different delay, if you will, but they're at the same frequency. And delay is really nothing more than phase. This little animated graphic here is just kind of illustrating what happens if we have a source that's putting out a signal, say the blue line here, going off to a load that is then reflecting that signal back. We can actually see that depending on the distance between the load and the source, that reflected signal may add up or constructively or destructively or in some complex way on that line. So this is part of what we can do in taking a look at characterizing devices with a VNA. So we'll have the VNA will have some kind of a source and apply an input signal into our DUT. And then some portion of that signal, ideally all of it maybe, would go through that DUT. But you may have some part of that signal that gets reflected off of the input port due to impedance mismatches. So the DUT's reflection, shown here in red, or transmission properties, shown in blue, will alter the magnitude and phase of the source signal. And this is precisely what a vector network analyzer will measure, both the magnitude and phase of the transmission and reflection of a signal being inputted into a DUT. This is a basic block diagram of a very simple basic vector network analyzer. So there's a source that's providing an RF signal. That source is going to come out through what would traditionally be called port 1 and get input to our DUT. There are directional couplers inside the DUT or bridges that will effectively pick off a portion of the signal that's being transmitted, and we'll measure that, as well as any energy that's reflected off of the DUT and comes back into port 1. That will get picked off by this sampler here and measured in this receiver. These receivers, traditionally called the R for reference receiver, and then the A and the B receiver, are going to measure the magnitude and phase, in this case of the transmitted signal, that's our reference, the reflected signal, okay, coming into the A receiver, and the transmitted signal coming into the B receiver. Those measured results of magnitude and phase are then collected and computed by some kind of a compute engine and put on our display in graphical form, most likely. The transmission properties of a device are going to be measured, by the B receiver, and basically comparing the B receiver results to the R receiver results, right? Because R is what we've transmitted, B is what we've measured through port 2. And this will typically be things like the gain or loss, through the device, whether it's an amplifier or a filter or a hunk of coax or something like that. It'll also measure an S parameter called S21 or S12. We'll talk about S parameters here in a moment. Also the transmission coefficient, which is just another way of referring to the S parameter, S21, for example, or even the insertion phase or group delay through our DUT. The signal that gets reflected off of the input and comes back in through port 1, these will be called reflection measurements. And reflection measurements are probably what we're most interested in most cases with the VNA. This would be things like the voltage standing wave ratio, or VSWR. Another way to represent the reflection properties is called the reflection coefficient, or S11. Also, we could refer to it as the return loss, as well as calculate the input impedance of what we see looking into our DUT. All of these things can be computed by simply measuring either the B results divided by R or the A results divided by R. Now, most professional vector network analyzers are going to have couplers both on the source, like we show here, as well as on port 2. Okay, so they may have this whole array of things here. The couplers and the source will be duplicated on port 2. But in the interest of cost with the NanoVNA, we typically only have it on one side. So what's a VNA good for? Well, for making single port measurements, we typically, we're looking at reflections. And this will be, again, SWR or VSWR of an antenna or an antenna system. We can measure complex impedance, as we mentioned. We can also measure components, or resistors, inductors, or capacitors at frequency. And with a little bit of additional mathematical transformation, we can measure things like feed line length or distance to fault. How far up my tower is my antenna broke or my coax broken? We can make some of these measurements by doing some additional processing on the reflection properties that are measured with the VNA. Now, if we are going to use the 2 ports of a VNA, we're measuring transmission properties. And this could be looking at maybe a filter and looking at the filter shape or the loss characteristics of a filter. If you're doing any homebrew work, that could be very, very handy. You might want to use it to look at loss in a feed line or delay through a DUT. Or maybe you want to look at the amplifier gain and frequency response, if you're homebrewing an LNA, for example. So all of these things mean that we can measure things like antennas and duplexers and diplexers, filters, various passive components, splitters and ballons and chokes. All of these things are very familiar items that we as hams will tend to use. And the VNA is really good for helping you characterize all of those things. So let's talk about S parameters. This is something that scares a lot of people off. S doesn't mean scary, but S stands for scattering parameters. Now, again, I know that doesn't really help you to define what that is, but let's see if we can clear up the mystery. The S parameters are simply a ratio of a measured response to a stimulus. And note the colors here. What we're doing is measuring the ratio of a response being applied at port X and being measured at port X in response to a stimulus being applied from port Y. Okay, so the X and Y stand for port 1 and port 2 typically. So S11 is simply the measurement of the reflected signal coming back onto port 1, okay, measured in the A receiver, with respect to the signal that is being applied through port 1, okay, measured in the R receiver. So that reflection is S11 is simply the measurement in A divided by the measurement in R, or A divided by R. It's as simple as that. Similarly, the signal that's being applied through port 1 and then being measured at port 2, that would be defined by S21. So it's the response measured at port 2 by the B receiver with respect to the signal being applied by port 1. So S21 is the response at port 2 with respect to the signal being applied at port 1. So inside the VNA, it's B divided by R, okay, R being, again, that reference signal. So that hopefully clears up a little bit of the mystery of what S11 and S21 are. And of course, there's also an S22. For a professional VNA, could be the reflection properties at the output of the DUT. And then S12 could be the reverse transmission properties if we had a source over here on port 2. But with a NanoVNA, we only have a source on port 1, so we're only concerned essentially with S11 and S21 in terms of S parameters. So another thing that can be confusing with any VNA is something called a user calibration. And so why do we need a user calibration, you might ask? It's like, well, we just bought this device. Wasn't it calibrated at the factory? Well, the answer is it was, but there's other reasons why we actually need to do a calibration. And one of those is that we've got a very, very large dynamic range, meaning even these inexpensive VNAs can measure very small levels of discontinuities and reflection properties and things like that in the presence of a large signal. So that very large dynamic range means we need to remove some what are called systematic error sources, and we'll talk about that in a moment. And also, we're going to be measuring phase. Remember I said that phase can also be considered as the delay. So if I use a piece of coax, for example, to connect my VNA to the device I'm measuring, maybe it's a filter, there's going to be some delay in that cable. So if I want to make an accurate measurement of the phase response of my filter, I need to be able to remove that phase that was introduced by my interconnect. Okay, so that's another reason why we want to calibrate, because we want to remove, those types of user added pieces. So we're going to establish what we call a measurement plane so that we can normalize, if you will, or remove the phase and amplitude response up to the point where I'm connecting to my DUT and establish that measurement plane right at the input of my DUT. So obviously those are things that can't be accommodated for in a factory calibration. It has no idea how you're going to connect up to a DUT, so you can't account for that. So there's a number of reasons why we need to do user calibration. So the next question is when? When do we need to do a user cal? Well, we really need to do that anytime we're going to connect up a different set of cables or adapters or fixtures from the last time we did a calibration. And the other primary thing is that if you change frequency range from where you did the last calibration, you need to do a new calibration over the new frequency range. Okay, so these are the reasons why and when we want to do a user calibration on a VNA. Now, it's not something you need any special equipment for, and it's a very simple process to run through it, but it is something to be aware of so that you don't get erroneous results. So again, as I mentioned earlier, a user calibration accounts for what we call systematic error sources. So where do they appear? So there's a class of error sources called tracking error. And this is the source and receiver, basically the source and receiver frequency response. They're not going to be perfect, right? They're not going to be perfectly flat. So if we measure those, we can then remove them from the measurement so that any distortion or variation in the source and receiver frequency response we can take out of our result. So what we're left with is just our DUT's result. We could also take care of source and load mismatch issues, impedance mismatch at the ports, primarily from the source and into the receivers. We want to remove any reflections that are due to the equipment itself, so we're only left with our transmission and reflection properties of our DUT. And then finally, you also got leakage and directivity, or the leakage properties, which is things like the directivity and crosstalk. Directivity refers to these samplers, if you will, these directional couplers. Ideally, this coupler, for example, would only respond to signals going this way and not respond at all to a signal coming back that way. But the reality is it may respond a little bit to signals in the undesired direction, and that's called directivity. And then also there might be some internal crosstalk between ports 1 and port 2, even if you don't have the device connected. Now, of course, that would essentially appear in parallel with our DUT, but if we can measure what that is, again, we can remove it from the results. And then finally, as I mentioned, any user cables or fixturing that we're going to use to connect to our DUT and establish that measurement plane right at our DUT connectors is the final reason that we want to do a user calibration. It's to remove these instrument systematic errors and to account for any user cables, fixtures, etc. So if we're going to use a VNA, what are some of the common measurements that we're going to make, and what display formats are they going to appear in? Now, typically when we're measuring things like the reflection coefficient, or S11, we're going to typically look at the response in a log magnitude response. So it's going to be shown in dB. And since we're looking at reflections off of the input of a device, there's not going to be any gain involved. So it's typically a negative number. Ideally, if it's 0 dB, that means that everything is being reflected off and coming back. If we're looking at something like minus 10 dB, that means that the signal coming back off the input is 10 dB down from the signal that we applied. If we set the instrument up to look at VSWR or SWR, we're typically going to show that in a linear ratio, 2.0 to 1, 1.5 to 1, etc., and show that versus frequency. Okay, that's kind of the most familiar thing that you might be doing with like your antenna analyzer today. Now, if you're going to use the instrument to measure complex impedance, oftentimes that's going to be represented on a Smith chart. Now, the topic of a Smith chart is a whole nother series of talks that we can certainly do at some point in the future, but that's typically how it's going to be represented, and it's certainly something that the VNAs can do. If you're measuring the transmission coefficient, or S21, that's very similar to S11. We're going to again be looking at the log magnitude response. Again, this could be a positive or negative number. It'd be a positive number if the device we're measuring has gain, like an amplifier, or it'll be a negative number if the device we're measuring has loss going through it. And of course, we can measure the delay, insertion phase, or group delay, and these things will typically be measured in a linear fashion, so many degrees in a vertical axis or something like that, depending on what parameter you're measuring. And as I mentioned, there are some transform measurements that can be made from the reflection measurements to give you some measurements versus time. And these would be things like a distance default measurement or a coax length measurement. Okay, it's often helpful to change, even though we're measuring the reflection coefficient like S11, if we change the format of that to be linear instead of log magnitude, we'll get a sharper peak in that result. It might give us a more precise measurement of a distance default measurement rather than have a little bit of a rounded peak in the trace that we'd be looking at. So with all that background on what a VNA is, now that we're all experts, let's talk about what the NanoVNA is. Okay. Now the NanoVNA actually started off life probably 4 or 5 years ago as a kind of an open source project. And so as a result, there are many developers, many variants, many manufacturers of what we can call a NanoVNA. The original, developed by a gentleman whose either name began with the letter H, Huygen, I believe it was a very small device. It still is available. Got a little 2.8-inch diagonal display. It's about the size, a little bit bigger than a credit card. Didn't even have a case on it when it came out. It's just a metal plate, that's sandwiched together 2 printed circuit boards and the SMA connectors here. And later on, some people started making an injected molded case for it as well. Okay, and that's typically called the original, or referred to as the NanoVNA H many times. And there are different color variations and things like that, but there are many different manufacturers, primarily in China, that just took this open source design and started producing it. Shortly after that came the H4, which is essentially the same design in terms of hardware design, except that it had a 4-inch display instead of the 2.8-inch display. And for my nearly 60-year-old eyes, that was definitely much better. In fact, most of the rest of the talk, we're going to be chatting mainly about the H4 because it's one of the more popular ones that's out there, and it's the one that we built this talk around. There was also another 4-inch version where somebody took the design and said, I could do a couple things a little bit better, a little bit different. And that one is called the NanoVNA-F, also with a 4-inch display, but instead of a plastic molded case, it has got an aluminum clamshell case, so a little bit heavier. A little bit better RF performance, and a couple of very small changes to the display, the user interface. But that's a pretty good unit, but cost about twice as much as the H4 if you're going to go buy one. And then we start to see now kind of the next generation of the NanoVNA is called the V2s. And the SAA, unfortunately, had this very cryptic name, the SAA-2. That's traditionally called the V2 or version 2. And they'll typically go up much higher in frequency. The original version's about the same size as the original NanoVNA, except that the SMA connectors come up off the long edge instead of the short edge. It's one quick way to identify them. And so, but it's a constantly evolving thing with these NanoVNAs. So as of kind of the winter 2020, 2021, early spring, where we are right now, I still kind of like the NanoVNA H4. It's very stable. It's got good support. There's a great user community out there. It's easy to get. And again, in US dollars, about $60. So still a pretty nice unit. I've got one right here that I too like to use. So it's about, if I hold it in front of me here, we can kind of see about how big it is. So, but also these same developers of the V2 are coming out with some better performing versions. So as of, again, about the last couple of weeks, the performance of the SAA2 is actually a little bit better than the H and the H4. There's an SAA2 with N connectors that's available, called the SAA-2N. That's also got a 4-inch display, okay, and N connectors. A little bit heavy because it's got a built-in battery and it's got a metal case. That one is, I've got now holding in front of me here, I've got one of these as well. And then most recently, the same guys started developing more improved units. And of course, the names don't get any better, but the more improved unit is called the NanoVNA-V2 plus 4. The first came out as the V2, then the V2 plus, and then the V2 plus 4 basically added a 4-inch display to the V2 plus. And these units are nice. They go up to 4 gigahertz, better dynamic range than the H4, but again, a little bit physically bigger, a metal case, and a couple of other differences. But that's a pretty good unit too. But again, cost twice as much as the H4. Okay, so again, depends on where you are with budget in terms of what you need in terms of frequency range. You help decide between whether you're going to go with something like the H4 or maybe the newer V2 plus 4. So let's go a couple more details on the NanoVNA. And again, the talk is mainly focusing on the H4 because that's the most affordable and probably the most popular. All of these NanoVNAs are what are called 2-port, 1-path. And that's basically the block diagram that I showed you earlier, meaning they've got 2 ports, right? Port 1 and port 2. Unfortunately, the NanoVNA calls it channel 0 and channel 1. That's really port 1 and port 2. Just unfortunate naming that the people who actually developed this thing probably never really used a professional VNA. They should have just called it port 1 and port 2, but they didn't. Okay. So they're 2-port, 1-path, meaning they've only got one path that has the transmitter, so it can only measure a through measurement in one direction, not the other. Now the NanoVNA H4 goes from a few hundred kilohertz, or actually about 50 kilohertz, up to 1.5 gigahertz. So it certainly covers most of the amateur radio bands that many of us will play with, certainly the HF bands and VHF bands without a problem. They offer standalone operation. It's got a built-in battery, can be recharged through a USB port. And all of them typically have got one or more PC applications available. So you can actually, instead of looking at the 2.8-inch or 4-inch screen, you can look at a larger screen on your laptop or desktop computer. And also that adds some additional features in terms of more trace points and some other measurement features that may not be available on the unit by itself. But it also tethers you to a PC, which kind of takes away from the nice portability of the instrument. But it certainly can be used either way. Place where to get a lot of details for all of the original NanoVNAs, you just go to this website here, nanovna.com. And that'll bring up, a short little list of places to go in terms of, some tutorials, as well as a link to the wiki and user group, which is this user group right here for all of the original VNAs. And very, very active, probably 15, 20 emails a day going through on the email list, lots of files. There's lots of folks that have taken and developed their own versions of firmware for these units. Some of them are really, really good. In fact, that are kind of the semi-official firmware versions now. There are separate groups for the V2 versions, and they can be found at this website here, nanorfe.com and nanovna-v2. And there's a whole nother set of user groups and things like that for the V2 versions, because it's a kind of a different, more advanced version of the hardware. So, take note of those links. And they're good places to go start, and really great places to get some information, and tons of materials both available in the user group file archives as well as the messaging archives that can answer most of your questions. So under the hood of the H and the H4, this is what's in there. Now this is just a higher level block diagram, but just to kind of show where things are. So channel 1 and channel 0, again, port 1 and port 2 in terms of VNA speak, but in terms of NanoVNA speak, it's called channel 0 and channel 1. That's where your device gets connected. The RF source to create the RF signal is a little SPI bus synthesizer. Anybody who's done any kind of homebrew work is probably familiar with the SI5351, very inexpensive SPI bus controlled synthesizer. There's a bridge that's used instead of a directional coupler to pick off essentially the transmitted signal and the reflected signal. So it's basically a return loss bridge. And then there's a set of mixers. There's actually 3 of the familiar SA612 Gilbert cell mixers that are used to take the RF signal itself, as well as the reflected and transmitted signals, and down convert them into essentially audio signals, audio level signals, which are then read by this very inexpensive stereo audio codec. A large part of what the NanoVNA is doing is leveraging some very high volume, very low cost integrated circuits for use in this unique application. This stereo audio codec is used in a lot of consumer electronics, audio equipment like CD players and things like that. So it was a very, very inexpensive chip to use and repurpose for this, to look at these RF signals by simply down converting our RF signals down into audio levels that it can read. And then all of the measurements that it makes, okay, are controlled by a simple microcontroller. And so that controls and reads data from the audio codec, as well as controlling the SI5351 and sending all the information out to the LCD display. And then, of course, there's some battery management capability and things like that to manage charging the batteries, and the user interface, little push buttons and things like that. So that's really all there is under the hood of the H and the H4. The V2 versions have a different architecture, okay, but functionally they're going to do the same thing, but they use some improved circuitry to get better performance. But again, not quite as inexpensive as the H and the H4. So let's take a look at the user interface of the NanoVNA. In this case, again, the original and the H4. There's a little jog wheel at the top. A jog wheel, you can rock it back and forth to things like to move cursors or markers back and forth, or to move up and down in menu items. And then you can push it to select things. Of course, it is a touch screen, so you can touch the screen to select menu items and also touch and drag to like move a marker back and forth, for example. And it's a fairly simple menu structure, regardless of whether we're talking about the H, the H4, or even the newer variants, the V, the V2, or the V2 plus 4. The menu structure is all very, very similar and almost nearly identical. Start off with a home menu, and then you break it down to go to various display functions like retraces and channels, marker functions, stimulus functions to set up the stimulus, etc. We'll go through some of this in a bit more detail later. There's also save slots where you can actually save your calibration results so that you can recall them later. So that if you've done a user calibration over a given frequency range to say measure your 40-meter antenna, you can save that off. So if you make some changes to the antenna and want to go back and remake the measurements again, you don't have to repeat the calibration process. You can simply recall the stored cal that you have. And of course, you've got a USB charging and PC interface. In the case of the H and H4, it's down on the bottom edge here. But that's basically what the user interface looks like and how you would actually go drive it. The newer V2 versions replace the jog wheel with 3 momentary push buttons, the center one being the select button, and then the left and right are essentially the same as rocking this jog wheel back and forth. So let's take a look at calibration. So we're back here. Yep. So most of the NanoVNAs typically have got 101 points across the sweep from your start to stop frequency. Okay, so 101 points isn't a lot of points. And so if we set up a very large frequency range, the spacing between each of those points is going to be your frequency span divided by 101. Okay, so you might say, well, why don't I just do a calibration from 1.6 megahertz up to 30? It'll cover my whole HF band. Well, if you do that, you're going to have a very coarse spacing of the calibrated points, and some of those you might only get 1 or 2 points that land somewhere within your amateur radio bands. So you have to kind of consider that. Most of the VNAs will try to interpolate the calibration between your calibrated points, but in all cases, it's always best to rerun a calibration over a particular measurement frequency range. Okay, so it's always a good idea to go ahead and redo that. So there are some other versions of firmware that we'll talk about later that increase the number of points, but at the end of the day, again, it's still always a good idea to set up a calibration over the frequency range that you want to make measurements over. So again, one of the software developers, firmware developers, when you go into the forums, you'll see this name, Dislord, and I'm not sure if it's just a username or avatar or something like that. But some of the versions of firmware he's developed have up to 401 points across the display. So 4 times the number of points. The new V2 plus 4s are just 200 points across. So let's take a look at the calibration. So the way to indicate or understand whether your unit is calibrated or not over the range you're measuring is these indicators on the left-hand edge of the display. Okay, the capital C right here means that we're calibrated for the current frequency range that I've defined for the instrument, and you're good to go. If it's a small letter C, a non-capitalized letter C, that means you've run a calibration that's over the frequency range, but not exactly at the same measurement points. Like I might have run a calibration from, 10 to 12 megahertz, but now I'm measuring between 10 and 11 megahertz. So the calibration points don't match, but the interpolation is going to try to do something. So it tells you you're close, but you're still not perfect. And then the number following the letter C is what memory location that calibration that you're using is stored in. Okay, so you can see and use that to recall later on. The rest of the letters indicate the various types of corrections that are being applied. The D stands for all the directivity errors have been applied to channel 0. R means that the reflection tracking errors have been applied to channel 0. And S means that the source match errors have been applied to channel 0. These are all reflection-based systematic errors, and then these are the corrections that can be applied. The T and the X stand for the transmission tracking error and the crosstalk tracking, or the crosstalk error. These are measurements that are derived from measurements on channel 1 or port 2. Now, all of these measurements here in green are required for all your measurements, whether you're making reflection or transmission property measurements. And these are really only required if you're making through measurements, like through a filter or through, measuring the, if you're actually using channel 1 or port to look at transmission properties. If you're only looking at reflection properties, like into an antenna, you don't even have to run that second half of the calibration to get these transmission properties if you don't want to. So let's actually look at the process of how you run the calibration. And it's actually a pretty simple thing. So on the main menu, if you just either touch the screen or push down on the thing, you'll bring up the main menu. And from here, you select Cal and start by hitting reset. And that clears out the calibration constants that are currently loaded. And then once you hit reset, go up and hit calibrate. Once you hit calibrate, you'll be presented with this menu here that first asks you to connect an open to channel 0. You connect the open to the channel 0. After you do that, then you touch short. It'll prompt you to connect the short, and then connect the load and touch load, and that'll run those calibrations for the open, short, and load. And then again, these are required for all the measurements. That'll help to generate those reflection or those correction terms that were shown in green on the previous slide. If you're going to be doing through measurements, you're going to want to do the following 2 calibrations for the isolation. For isolation, you're essentially putting a load on channel 1 to kind of terminate and the signal there, so that channel 2 shouldn't be seeing, or channel 1 shouldn't be seeing any input. And then the through measurement is when we're connecting up channel 0 to channel 1 to measure through, to look just again for the transmission tracking measurements. Once you've done all these calibrations, it's a pretty simple process. You hit done, then it'll prompt you to select what slot you want to save things in. And that slot 0 is special, because whatever you save in slot 0 is what gets recalled when you power the unit back up again. So if there's a common measurement you make all the time, You can save that to slot 0, and then as soon as you turn it on, the instrument's ready to go. And ideally, we want to connect all of those calibration standards, the open, load, and short, to the same location where your device under test would be connected. And that establishes that measurement plane that we mentioned earlier right at your DUT connector. So the calibration, let's talk about what we mean by calibration plane and port extension. So let's say I've got the VNA, I'm connecting up to my DUT. Ideally, we want to connect our open, load, and short to the same place where our DUT would be connected, so that the phase and amplitude at that location, at the end of that cable, is what we're calibrating out. Okay. So again, that removes the phase of the connections as well as any other frequency response issues there might be with those interconnects, so that we can actually establish that measurement plane right at our DUT ports. Sometimes, unfortunately, that's not possible. So sometimes you might need an adapter or another little bit of coax or a fixture or maybe even a circuit board trace to get to the point where we actually want to make the measurement. So one way to account for that is to do something called port extension. Port extension says, okay, I made my calibration measurement at this location, but I really want the measurement to be made somewhere further down the line. Okay, so we call that port extension. So as long as that additional connection down to where the actual measurement plane wants to be is a continuation of that nice 50 ohm environment, you can use this thing called port extension. Now, unfortunately, the NanoVNA calls this electrical delay and not port extension. Most of the professional VNA world calls it port extension. Okay, but we can still very simply use this. And what we're going to do is essentially adjust this by using an open or a short at the DUT location. So like if I got maybe a printed circuit board trace going down to a little patch antenna on a circuit board, I can momentarily short out at the input of that antenna and use that short to establish what that electrical delay is. And we can do this by looking at the Smith chart, because a short, for example, on the Smith chart is all the way over at the 3 o'clock position. Okay, so if we have some delay going to that point actually gets rotated around the chart. So by simply shorting out at our desired measurement plane location and adjusting the electrical delay parameter in the instrument until that short returns back to the 3 o'clock position, now we've established the appropriate electrical delay for the amount that we're extending and moving that measurement plane. Again, this is really only important when you must have an accurate phase measurement, for example, to measure a complex impedance at a particular location, for example. If you're just hooking up a hunk of coax to measure an antenna that's up on your roof or something like that, you generally don't have to worry about this. So when we talk about the NanoVNA, we talk about channels and traces, right? We've got channel 0 and channel 1, which are our reflection and transmission properties, or channels. And then we can have various traces that we can have up. You can actually have up to 4 traces active at a time, okay? So again, on the channel 0 is our reflection port. From the VNA parlance, it's called port 1. And this is the port that's used to measure S11, reflection coefficient, SWR, input impedance, etc. And then obviously channel 1, which is port 2, is used to measure S21, gain and loss through a device, group delay, etc. So the traces, again, you can have up to 4 traces, and each of those traces can be assigned to either of the 2 channels. So I can have all 4 of them assigned to channel 0 to measure maybe S11 and SWR and input impedance all at the same time on 3 traces, for example. So you can pick and choose which traces you want active and which channel you want those traces attached to. Okay, so you decide you can have a very simple display, just measuring SWR, and that's it. Just by turning on, say, trace 0, connecting it to channel 0, and then turning off all the other traces and just use it as a single trace instrument like a traditional antenna analyzer. So what are some of the common trace formats? We mentioned a little bit about this before. Again, we go through display to trace and then select format, and we can choose what format we want. For channel 0, for our reflection measurements, again, typically if we've got it set up to look at S11, that's typically using a log bag format. If we're looking at the, the Smith chart, we might look at complex impedance. SWR will typically be a linear. So you pick, what function you want that trace to be, and then whether you want to be a linear, an imaginary, and then impedance and things like that. So you can go pick and choose what format you want those traces to have. For channel 1, for the transmission properties, again, log magnitude for S21, phase, etc. These are all the different measurements that we can make off of channel 1. So you just go pick that through the trace format menu. Okay, so there's additional ones for doing some more advanced work, but we won't cover those. So the other thing that's important is to set what's called the source. The source is the RF source that's inside the NanoVNA. We want to set the frequency range we're going to go measure. There's a couple of ways to do it. You can set the start and stop frequency. Maybe I want to measure from 14 megahertz to 14.3, right? That's setting the start and stop frequency. You could also, instead of doing that, set the center frequency and span. This is very similar to what you do typically on a spectrum analyzer. And if you're measuring a filter, for example, you might set the center frequency of the filter and then the expected span or bandwidth of the filter to measure it that way. So you have your choice of setting up the frequency range that you want to measure over by either using start and stop or start and span or some combination of the others. Okay. CW frequency will turn the instrument into a single frequency source, and that might be used if you just want to, maybe set up a single frequency to measure impedance at a certain frequency or SWR at a certain frequency and then go make adjustments. You can do that. Okay. So on the VNA itself, there are 4 markers typically. I think some firmware versions offer more, but most of them offer 4 markers. And they show up as these little inverted triangles on the traces. And they'll have a little number in them indicating which marker it is that we're talking about. The marker values will appear up on the display. So on the top of the display here, for example, what we see is, I see the yellow trace is assigned to channel 0, which means it's a reflection trace. It's showing log mag, which means that this is the log magnitude of S11. That's what the yellow trace is. 10 dB per means that each division is 10 dB per division. And then the active marker, the one I just most recently touched, is shown right here. So in this case, the active marker is marker number 2. You see the 2 right here. So that's this marker right here, and that's showing that that marker is at minus 8.19 dB, right? Because the little diamond here indicates that's my reference level, so that's 0 dB. So there's 8.19 dB down from there. So channel 0, for example, the green trace, that's on the Smith chart. That's on this curly Q chart here. That's this trace right here. Again, in this case, it's showing the complex impedance at marker number 2 is 22 ohms and 50 picofarads. Obviously, then all these are all on channel 0. The blue trace here is channel 0. That's on SWR. Okay, and that's the SWR trace down here. And again, it's showing SWR 1 per division. So this is 1 to 1, 2 to 1, 3 to 1, 4 to 1. Okay. So the marker markers will move back and forth in frequency using the jog wheel. The selected marker is shown here. And then if I have more than one marker up, I get a delta marker, which will give me the difference between the active marker and the one that it was active prior to that. In this case, since I only had 2 markers up, this is showing me the delta, in this case, the delta in frequency between marker 1 and marker 2. All markers track each other on all the traces. So if I move a marker, on trace 1, that marker will also move on all the other traces that are active at the same time. And there's also search features for the markers themselves that allow you to search left and right for min and max, look for a peak, look for a dip, that type of a thing. And there's also operations. The operations allow you to say, maybe I'll move a marker to a frequency and then tell it, I want to change the center frequency to where that marker is. So you can actually do a marker to center. Okay, and that basically says that I'm going to take and change the center frequency that I'm measuring to where the marker is. And of course, you can also tell it what you want the markers on the Smith chart to read. Do I want them to read complex impedance? Do I want them to read resistance, inductance, and capacitance? You select that by selecting this menu item. So here, how do we go to set up the NanoVNA to actually go do something? So typically you are going to first configure the traces, what channels you want those traces are on and what format you want. Okay, maybe I want a channel to show my S11 and another trace to show SWR. So I'd set both of those to channel 0 and set those two formats, log mag and SWR. Then I also want to set up the stimulus. What frequency range do I want to go measure over? Start and stop or center and span? The order of which you do those things really doesn't matter. You can do one or the other. You don't really have to start one way or the other. But once you've done those things, then you're typically going to run a calibration and save it. If you've already performed a calibration, the calibration also saves these things as well. So if you're always going to make just an SWR sweep of an antenna over a frequency range, set up those channels and traces, set up that frequency range, calibrate and save it. And then as soon as you recall that thing, all of this is already done for you. So you only really have to do it that one time. So all of these things are saved as part of that calibration save slot. And then of course you connect your device and you test it. You get your results. Maybe you'll throw some markers on there, extract some measurements off, things like that. And maybe even adjust traces and formats as needed, because even if I add a new trace and new format or something, the calibration all still holds. So you can actually bring up different traces and look at things at will, just to kind of simplify what that display looks like. But that's the basic process of how you set up and use a NanoVNA. So here's a couple of examples of what the display might look like. Now in this case, maybe I want to measure an antenna, right? The antenna I'm going to connect to channel 0, which is port 1. That's the one that's got a source on it. I'm measuring essentially S11. So this graphic is showing me that I'm measuring a reflection back into that port. And we can see, again, I've got channel 0 is a log mag trace. That's the log mag of S11. That's that guy right there. The green trace is on the Smith chart. So that's this little curve thing, which is plotting out the complex impedance on the circular Smith chart. And then the blue trace is SWR, and this is showing my SWR curve. And as you can see, my frequency range down here. So there's our frequency range from 7 to 7.3 meg. I was measuring my 40 meter dipole in the phone portion of the band. So there's my SWR, there's my complex impedance, there's the reflection coefficient. And you can kind of see that it all maps up to the colors here as well. And of course, I've got one marker up here. I should have moved the marker before I took the photo. The marker is just sitting right at 7 megahertz, and I can see the value of where that marker is on each of those traces. Now let's say I was measuring a filter. Maybe I'm homebrewing a filter I'm going to use inside of a transceiver, or maybe a filter that I'm going to apply at the output of a homebrew transmitter or something like that. In this particular case, it's a low-pass filter that I designed to put at the output of a Michigan Mighty Mite color burst crystal based CW transmitter. So it's a single transistor transmitter. It's got lots of harmonic distortion, so we want a low pass filter to knock down the second and third harmonics and higher harmonics. So in this case, I've got channel 1 or channel 0 and channel are looking at the log magnitude. Okay, that's the S11. So it's better than 10 or 15 dB, down from 0. So that's actually pretty good. I can look at the purple trace here. That's my SWR. That's all well below 2 to 1 over my passband. Notice I'm starting at 1 meg, going up to 15 meg here. So up to about 4 megahertz or so, I've got a really nice looking SWR looking into the filter. Now in this case, I've got channel, the blue trace, channel 1, is the transmission properties through my filter. So I can see I'm actually sitting near 0 dB through the passband of the filter. That's good. And then we could see it rolling off as I go higher and higher in frequency. In fact, the marker is sitting here at about 10.5 megahertz, which is about the third harmonic, which is the highest harmonic coming out of this little single transistor transmitter. You can actually see that at that marker location, this filter is going to attenuate that signal by about 47 dB. So it's going to knock down that third harmonic by 47 dB compared to what it would have been if I didn't put the filter there at all. Okay, so again, that's showing me the effective insertion loss of the filter, and again, the SWR and reflection coefficients, looking at the input of the filter. So here I'm looking at a combination of both input reflection properties as well as the transmission properties of a homebrewed low-pass filter. Okay, and I've also left the complex input impedance looking here. I probably could have taken that one off because I really didn't use that plot for anything. I probably should have taken that off, and just simply removing that trace would have removed that. So measuring coax length, here's another example. This is using what's called the time transform. It's in the menu structure. And the time transform is actually measuring reflection properties, because if I have a hunk of coax with an open at the end, all the signal that goes into that coax is going to reflect off the end and come back. Okay. And by looking at the reflection versus frequency, we can then do some calculations to determine the delta T, how long it took that signal to come back. And then if we tell the NanoVNA what the velocity factor of the coax is, we can actually get a measurement of distance to where that marker is from the beginning. So in this case, I had a little over a 9-meter length of coax that was open at the end that I stuck here. Now, of course, if we connect the other end of the coax up to port 1 and turn the transform off, we can then measure, loss of the coax over frequency. Okay, you just don't do both of those at the same time. So with that, again, very inexpensive device. And it's certainly not perfect. So I like to call this slide the good, the bad, and the ugly. You might remember that old spaghetti western with Clint Eastwood here. Cue the music. So so there's some limitations and downsides to a $50 VNA compared to a $10,000 or $15,000 VNA. Let's take a look at what some of those downsides are. One of the biggest ones is, again, only 101 trace points. Again, using external software connected up to the VNA can often help that one, as does later third-party firmware. I guess I mentioned Dislord. They've got firmware for the H and the H4. They'll give you up to 400 points. The NanoVNA V2 plus 4 has got 201 points, but it's still a relatively limited number of trace points, which really affects, the ability to look at really wide frequency ranges with good resolution. So you may kind of make multiple measurements over narrower frequency ranges. But again, using the external software, you can help because it will actually make measurements over sub ranges and then put it all together in one plot for you. Now on the H and the H4, the output of the device is not a pure, nice, clean RF sinusoid. It's actually a square wave. That's actually what it looks like on a scope. Okay, it's about a 600 millivolt peak-to-peak square wave into 50 ohms. And it only goes up to a couple of hundred megahertz. Okay, so it only goes up to about 300 meg. So if you're making measurements above 300 megahertz, the instrument actually uses the third harmonic, right? Because a square wave, as you may know, if you look at the frequency content of it, like shown up here, you've got a lot of energy at the fundamental. You've got a lot of energy at the third harmonic, the fifth harmonic, the seventh harmonic, etc. Essentially, a square wave is a collection of the fundamental and the odd harmonics. So the inexpensive H and H4 actually take advantage of that, okay? And so when you're making measurements up to 300 meg, we're looking at the fundamental. From 300 meg to 900 meg, it uses the third harmonic. And from 900 meg to 1500 meg, it uses the fifth harmonic. So, well, you say, why do I have to worry about that? Well, look at the device you're testing. Will the device you're testing have a problem with the fact that the input is actually a square wave and has spectral content other than the frequency that you actually want to measure? You might have to consider that, especially if it's a homebrew circuit or something. So this guy right here is a 200 megahertz square wave that I took a sample of here. That's the same exact output you get if you're measuring at 200 meg, or at 600 megahertz, or at 1 gigahertz with the NanoVNA H4. Okay, so all three of those frequency ranges have got this exact same waveform. And of course, and also on the H and the H4, the output power is not adjustable. Okay, so from 50 kilohertz to 300 meg, the power level is about +2 to 0 dBm. Okay, so about a milliwatt, a little over a milliwatt. Okay, from 300 meg to 900 meg, we're looking at the third harmonic, and that's typically about 10 dB lower. Okay, in terms of output of power. And then the third harmonic, or excuse me, the fifth harmonic for 900 meg to 1.5 gig is another 10 dB or so lower than that. Okay, so you might say, well, okay, if I'm testing, I've got an amplifier that I built for 1.2 gig. Just remember that if you're testing it with the NanoVNA, that's also being hit with energy at 600 meg and at 200 meg, in addition to the signal that you actually want to measure. So you do have to consider that. And since you can't adjust the output power, okay, you've got to consider that, is this level of square wave being applied to my device going to be okay for my device? All right. Again, so is that going to be correct? And because I can't adjust power, it means I can't make some of the other traditional VNA measurements like gain compression and things like that. And also the input level to the NanoVNA into channel 1 is not adjustable. So if I have an amplifier that's got 25 dB of gain, I might have to put a attenuator on the output of that preamp or the output of that amplifier before I put it into the NanoVNA, and then just account for that, because you may overload the input if you get too large of a signal into channel 1. It also has a relatively limited dynamic range. The H and the H4, typically 40 to 50 dB dynamic range. Okay, the V2 and the V2 plus 4 are better. They get closer to 60 or 70 dB, or sometimes better than that, depending on where you are. But again, this doesn't approach like the 100 to 130, 140 dB dynamic range you can get on professional devices. And really, it's going to be mainly an issue if you're trying to look at maybe high rejection devices, such as like a duplexer for a repeater, for example, where you might want to try to measure 100 dB of isolation between transmit and receive frequencies. That'll be a little bit tough to do on a $50 NanoVNA. The resolution bandwidth in the result is not adjustable. That also affects the measurement dynamic range and the noise floor of the instrument itself. Again, so there are some third-party firmware versions that help with this, that actually do some other bandwidth, resolution bandwidth reduction in processing. So Dislor, for example, has got adjustable RBW to some extent in their firmware. And there may be some other limitations as well. But again, some of these don't really apply to the V2. The V2 unit does use a sinusoidal output, so it doesn't have these problems with using harmonics. It actually uses a fundamental, pretty decent looking sine wave, still not perfect, but it is a sinusoidal output over the whole frequency range. The V2 plus 4 goes up to 4 gigahertz, and it's a sinusoid all the way up. So that's good to know. So again, these limitations are primarily on the little inexpensive, $50 units. So a quick summary, I call the NanoVNA kind of the RF tool or toy of the year, because at this price point, why not, right? It's less expensive than a lot of the, just dedicated antenna analyzers that are out there. I've got one of these, Rig Expert AA55, goes up to 55 megahertz, does a lot of the features that the channel 0 port does in terms of things like Smith charts and SWR plots and things like that. But it's only a single port device, not a 2-port device, and it costs 5 times as much of the NanoVNA. Now, which one would I bring outside and use outside? Would probably be this one, because the inexpensive NanoVNAs, the display isn't that great in direct sunlight, that type of thing. But again, for $50, it's a pretty amazing tool. So really amazing capability for the price. There's a ton of videos and things out there, not only on my YouTube channel, but elsewhere, in terms of how to use it and how to get the most out of it. And some very, very active user groups to help answer your questions in using the device. Now, of course, I put this talk together originally for us here in the US. So it was a pretty good US source for these was R&L Electronics in the US. I'm sure you've probably got a good source in the UK as well, but I'm not familiar with where you guys would normally get your good ham accessories, but you can do your own research there as well. So with that, let me know if any questions came up in the chat here. A little bit of a shameless plug for my channel. I've got about 10 videos on my channel just dedicated to the VNA, the NanoVNA itself. That's among the 300 plus videos that are there. Certainly you can go find those videos there. There's a whole playlist for just the NanoVNA that might help get you started as well. With that, David, I'll open it back to you, see if there's any questions, and we can go from there.
Thank you very much, Alan. We certainly had a few questions asked as well and lots of nice comments, and it's a complex subject covered really well. So I'm sure you might have questions. If you'd like to ask a question and haven't already done so, then please do it now on either the YouTube chat or the BATC messaging. And don't forget to include your first name and your call sign as well if you've got one. But now, Alan, giving you a chance to have a quick drink, which you've well earned. Let's start with the first question, which comes from Ian, GM4VXM. And he says, can NanoVNA be used as a signal generator producing a sine wave without harmonics or an output connector? And if so, what is the maximum frequency? I know you've answered a few things recently, but that was asked fairly early on in your talk.
Yeah, so Ian, as you gathered, the inexpensive H and H4, the output's a square wave, so you'd have to put your own low-pass filter on it if you want to use it as a continuous device. And then, so you might say, well, then the V2+4 might be a good one because that gives you a sinusoidal output. Well, that's good. However, the V2+4 doesn't leave its output on continuously. It pulses on and off. So it also would not be a good signal source. So the one in the middle, the SAA2, 2N, for example, that one actually would be a half decent source for a continuous wave, CW signal source. The other thing that I'll mention, kind of a sister product to the NanoVNA, you may have seen, is called the Tiny SA, which stands for Tiny Spectrum Analyzer. And the Tiny SA does have a mode where it can give you a continuous sinusoidal output. So that's also about a $50 or $60 device, nice little spectrum analyzer that fits in the palm of your hand. So that's also a potential source for a continuous wave, low power RF source.
Thank you, Ian. You talked about the various versions, and some of the chat that's been going on as well on YouTube and on BATC talks about the various versions and where to buy the best one. Some of these versions, you say the hardware is broadly the same from what I understand, but the firmware is different. So does that mean if you've already bought one, you can upgrade it safely to have some of these extra features?
You can. Dislord, for example, that's the firmware that I'm running on my little H4 here. I run the Dislord firmware on mine because it adds the ability of having 400 trace points and a couple of other nice features. But if you decide you don't like that, it's very simple to revert back again. And there is a video on my website that talks about how to update the firmware on this one. I didn't do videos on how to update like the SAA2N. But that one is actually pretty easy as well. You use that offline software and you can update the firmware that way. So you can always try out these versions of firmware. If you don't like it, just go back again. And the process isn't a simple one-step process. There's 2 or 3 steps involved in doing it. But once you've done it once, it's actually pretty simple and very easy to go back and forth.
Okay, great, thank you. And now Mark M7BRR says, I've looked on Amazon and Net for getting a NanoVNA, but I see that there's many different companies selling what seems to be the same thing. So are they all as good? I guess that's similar to the question I just put to you, but can you address that for Mark?
Yes, Mark. Unfortunately, especially with Amazon or eBay, you don't really know the source. And the reality is that for like the H and the H4, there are probably a lot of different manufacturers that are making these things. So that's why what I would recommend is talk with your fellow club members and things like that. And if you got a reputable ham radio dealer that sells rigs and things like that, usually they're going to try to seek out the sources with the good high quality devices. Because if you just go randomly to eBay or Amazon, you might be taking a little bit of a risk unless you say you've got a buddy that has picked up one and it performs well and this is the manufacturer that it was, and go to this link and go buy it. Because there's nothing to stop anybody from building these things and selling them because it is kind of an open source design.
By the way, looking at doing a little bit of research before tonight's program earlier on, I found them on eBay and Amazon in the UK, and they did vary from just over £40 currently to like 4 times that price. So it is quite difficult to tell, and they were all for the one with the 2.8-inch screen as well, so it can be quite difficult from that. So maybe if I could ask anybody at home who's recently bought one, and found a really good source. Feel free to put that on the web chats, either on YouTube or BATC, and I'll relay that to everybody here. Got another question now from James Kelly. Says, can you calibrate across most of the HF band, i.e. run the cal with a sweep from 3 to 30 megs, or is it best to cal on a focused area of interest with a smaller BW, which I guess is bandwidth, i.e. a 4 megahertz centered on 7 megs?
Well, it's good. James, again, it comes down to the fact that depends on a little bit on what firmware you're using and what you tend to get out of the measurement. So a 3 to 30 megahertz cal, you're covering 27 megahertz. Divide 27 megahertz by 101 points, right? And that tells you the frequency spacing between each of those points. And you might find that only 1 or 2 of those points might land in a particular band of interest. So you may not have a good calibration across that particular band. If you just want to look at good broadband characteristics, then that's fine. But if you really want to run a cal and then make a measurement on a 20-meter antenna or a 40-meter antenna, you're really better off probably doing a calibration over that narrow antenna. That being said, if you're using some of the external software, one of the popular ones is called NanoVNA Saver. NanoVNA Saver will allow you to define that larger calibration range or frequency range, 3 to 30, and actually make the measurement using multiple 101 point segments. So you can get a higher resolution in frequency spacing across that wider range. But that would require you using the PC-based software. And then you can kind of get away with that, because then you'll have enough density in points or resolution in points and frequency to get good results over your narrower measurement frequency ranges.
Okay, that's good, thank you. We've had somebody recommend Murfield Electronics in the UK as one of the retailers of a good VNA. They advertise in Radcom, and they sell approved VNAs, they say. So that's good. Thank you for that. If you've got any other good tips based on your own experience, that would be good to hear them as well. From Keith Lockstone now, I want to explore ferrite choked antenna feeders on the bench. Is there a way of simulating an unbalanced dipole using single components?
Yeah, so simulating unbalanced things, again, you're typically going to need some kind of a balun to do that. The one good thing is that the VNA, because it's battery powered and it's small, you can almost consider the output being unbalanced, right? Because the ground on the shell of the connectors is not connected to Earth. Especially when you get up higher in frequency, you might really need to actually build your own, maybe even a 1-to-1 balun in order to get a good balanced to unbalanced measurement result there. But this is actually something that's been discussed fairly extensively on the email lists through the user groups. So I would probably defer to going and searching those user groups for making unbalanced measurements or balanced measurements. There's actually a lot of chatter that's been going on through there to talk about good measurement techniques and calibration techniques to get good, accurate results on unbalanced situations. Okay,
great, thank you. Over on BATC now, Brian G8DKK has said cal kit parts using ideal standards. Any workarounds for that?
Well, the calibration kit that typically comes with these things is typically an open, short, and load. The open and short are pretty basic. The quality of the load in terms of how accurately it's 50 ohms and how good of a 50 ohm resistor it is over broadband will tend to vary. Oftentimes they're not really the greatest things. And compared to, say, a professional calibration kit will often have additional terms associated with an open, load, and short. And these account for things like what are called like fringing capacitance and things like that to better characterize that load over a much wider frequency range. The loads that are typically used or the cal standards that are used for the NanoVNA are considered really ideal. But for the level of performance that the NanoVNA gives you, they're probably good enough. And the corollary to this, or the other typical question that we'll often get is that, well, why do I need an open, right? What's a calibrated open? What does that mean? Okay, can I just leave the connector off? And the reason we actually have an open is because of as I mentioned, this calibration plane issue. Part of the calibration plane is to establish where the phase of the signal right at that measurement point. So if we connect a 50 ohm resistor at that point, or we connect a short at that point, but then if we remove and have an open, if that open is physically further or closer in or further away from the device, the phase of the open might be different. So a calibrated open actually establishes that right measurement plane. So you might say, well, why do I need an open? That's why, is to get a good, accurate measurement of that measurement plane when you're actually using the open and short primarily. But again, the open and shorts, they're generally pretty easy even to build or to go buy. The 50 ohm loads, you might be better off actually searching for a good high quality, SMA load, for example, to use as your own load. Because I found that at least on one of the VNAs I bought, the 50 ohm load was more like 49.2, wasn't really that close to 50 ohms. So I wound up using a higher quality one that I had.
Yeah, really good information. There's a lot, as I said to you before, Alan, lots of compliments. Dave G0DDF says, thank you, Alan, for a very informative presentation. I do subscribe to your YouTube videos and found them very well presented and very useful.
Thank you.
Lots of other people saying similar thing. Stan M0HYY says, I've read on the internet where users have damaged their NanoVNA front end. I presume this would be caused through static discharge. How do you protect this from happening?
Well, I haven't had it happen to me, knock wood, okay, but I would think that if you're measuring, it would mainly be, I would think, if you have got a large wire antenna up in the wind, and you can get a static charge built up on the wire. In that case, it's always a good idea to kind of short that connector out before you make the connections. But if it's something that's continuously happening, like you've got a very windy day or something like that, and you're getting the static built up, once you connect to the VNA, you're presenting essentially a 50 ohm load that will often dissipate the charges before they have a chance to build up. But it's really just a matter of trying to discharge things before you make the connection. And same thing if I got something I'm working on the bench and you've got a very dry environment, it's in your house or your shack or something, just take good anti-static practices in terms of keeping yourself grounded and things like that before you connect up a device. I don't think it's that common to actually have static damage, but I can certainly see that it's possible. So.
Okay, that's really good, Alan. At this point, I just want to remind everybody watching as well as this excellent presentation tonight, the RSGB have recently introduced some very good practical videos, and we can show you now a link to where you can have a look at those. And one of those videos is also about setting up the NanoVNA, so you'll find that useful as well. The link is on your screen at the moment. We've got some more questions for you, Alan, here. Rod VE7WVI says, great presentation, Alan, thank you. How useful is the NanoVNA for measuring capacitors and coils?
Well, actually, I think it works pretty well. The trickiest thing is the fixturing that you might need to connect the capacitors and coils to the VNA itself. Because you don't want the fixtures to add too much to that, especially if you're measuring very low values. So you might have to build up, a couple of little fixtures and then make your own calibration standards. Okay, so let's say I'm working with some very small, axial leaded components. You might use little pin sockets or something like that to make the connections. So you might have an SMA connector coming out to maybe a small bit of circuit board with these connections on it. And then you might actually, maybe use a 50 ohm resistor and then a short piece of wire and an open to run a calibration to those sockets, so that when I make the measurement, I'm only making the measurement on the device. And then the second thing is to also ensure that you're making the measurements at the appropriate frequency range for that device. As you may know, that inductors and capacitors, for example, will have a self-resonant property, okay, or frequency. So above that frequency, they're going to behave like the opposite component, right? So capacitors look like capacitors at low frequencies, but as the frequency goes up, the parasitic inductance of the capacitor itself at some point will dominate, and then the capacitor will look inductive. So you want to ensure that you're making the measurements at an appropriate frequency. And the best thing to do with that is to start at a lower frequency and work your way up. and it'll become obvious if you're looking at the impedance whether you've actually changed state on it. But it can be used pretty effectively to measure devices, and I've actually made some measurements on, surface mount inductors and capacitors, and compared that to what I measured on professional equipment. And within the frequency, as long as you're staying away from that self-resonant point, the results are actually pretty good.
Yeah, that's good. Thanks very much, Alan. I'm just looking at all of the chat that's going on here. All really good stuff. Lawrence, though, says that the H4 is showing out of stock at Murfield at the moment. Sad face. Thanks. Terry G3 VFC says, thanks, Alan, for all your videos on VNAs and Smith charts. Someone else, Bruton UK, says he just ordered an H4 for £69, which I guess is probably about $80, something like that for you in your money at the moment. We must thank, by the way, Richard G4 KRW says he has no connection with Murfield Electronics, but he's the one who recommended them. David Holman, M0YDH, says, I connected my new V2 to my regular phone charger. The battery doesn't store charge now. Is there a charge current limit that applies? And do you have any ideas about that, or replacement batteries or anything, he says?
So what I found with the V2s, because oftentimes they ship without a battery, the battery management IC in there needs to, I'm trying to remember the process here. If you just plug a new battery and you turn it on, it won't come on. It's like the battery is discharged, even if you know the battery is charged. So you actually have to, there's a process that's actually in the manual, and I believe you actually have to turn the unit, have the unit turned on when you plug it in or something like that. There's something about the battery management system actually has to see the battery first before the charger, or vice versa. But it's in the user manual for the V2, because if you reverse it, it'll look like you plug it in and it's not charging and you don't know why. So, but there is a little process that has to kind of wake up the charge management IC, and it's an order of things. So you should be, hopefully that will take care of it.
So hopefully the batteries are okay, but it's just that you need to sort of tell the thing that they're actually okay. It's
good, getting it going in the right order. Yeah.
Right. Okay. Almost finally, I think now. So if you have got any questions, you need to ask them really quickly now, because we're getting to the end. James Kelly comes back again and says, dare I ask, measure for resonance or SWR, or does it not really matter? He says, question mark.
Well, it's a good question. So one thing I talk about a lot, and people ask me questions about, is that a resonant antenna doesn't always mean that's the lowest SWR. Okay. The lowest SWR and lowest return loss, okay, again, doesn't always correspond to resonance. Resonance only means that's the frequency at which the capacitive or inductive reactance has gone to zero, that the input impedance is purely resistive. But that purely resistive impedance doesn't necessarily correspond always to the lowest SWR, lowest return loss. So if it's me, okay, I will typically tune for the lowest, the best return loss, okay, lowest SWR to get the best power transfer. That doesn't always mean resonance.
Okay, I think that's hopefully helped him as well. I think we really are pretty much at the end now, Alan. I want to thank you very much indeed for tonight. I did actually scribble some notes of some questions myself, and one of the things I was going to say, although we're all getting used to these wonderful electronics that you can get, it can't just be me that gets these things, and there's absolutely no instructions in the box whatsoever, not even how to switch them on. So a video and a presentation like you've done tonight, and the videos that you're on your website, and it is an excellent website, by the way, to have a look at. I know you couldn't say that yourself, but it is, and just look for Alan's call sign on the web, on YouTube, and you'll find lots of videos that you've done to help us in the amateur community. But Alan, once again, thank you very much indeed for tonight.
All right, thank you very much, David. Thank you for having me. 7-3.
7-3. There we are, and thank you very much again to Alan. That concludes this webinar, and of course we want to thank our guest presenter, that's Alan Wolke, W2AEW. Well, we hope you've enjoyed this Tonight at 8, and that you'll join us next time when we'll be finding out more about amateur radio direction finding. And if you'd like to see details of that and other webinars, or to send any comments or feedback, please visit rsgb.org/webinars. And remember, if you subscribe to the RSGB's YouTube channel, you'll also be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. But we end this evening with a few moments silence to remember His Royal Highness the Prince Philip, who died on Friday the 9th of April 2021. He was the patron of the Radio Society of Great Britain from 1952 to 2021.